Some of Earth's most spectacular landscapes are high-elevation orogenic plateaus, like the Andean altiplano and the Tibetan plateau. Yet, how these features form, how they evolve, and what happens beneath them is still poorly understood, despite important implications from paleoclimate to mineral resources. One way Earth scientists study the deeper levels of plateaus is through geophysical imaging. Geophysical surveys have shown that the crust of Tibet is doubly thickened, up to 60 to 80 kilometers, and the mid-crust of Tibet may be partially molten. These images have inspired thermomechanical models to simulate the orogen and make predictions about particle paths and pressure-temperature time paths that rocks will follow. These models can be tested and constrained through analysis of exhumed rocks from deep within the orogen. However, these rocks are rare, often limited to xenoliths and the cores of gneiss domes. One more line of evidence that we can use to study plateaus are ancient analogues, old mountain belts where the deep crust of older plateaus is exposed today. For example, the Appalachian Cladonide mountain belt, a classic collisional orogen, may be a good place to find ancient plateaus. And indeed, one has recently been recognized in the New England segment of the orogen. Three major orogenic phases are recognized in New England. The earliest is the Ordovician Tectonic orogeny, interpreted to represent arc-continent collision. This was followed by the late Silurian to Carboniferous Acadian orogeny, associated with the collision of the Avalon and Maguma terrains and generally regarded as a dominant event in New England. And finally, the late Carboniferous to Permian Alleghanian orogeny, interpreted to represent collision of Laurentia and Gondwana in the final assembly of Pangaea. The effects of the Alleghanian were rather limited in New England, so today we'll focus on the Acadian. Several lines of evidence suggest the existence of an orogenic plateau in the Acadian orogeny. Geochemical crustal thickness proxies suggest a doubly thickened crust, on the order of 57 to 70 kilometers, similar to modern plateaus. Thermobarometry shows similar pressures across much of southern New England, suggestive of a low-relief plateau. And thermochronologic evidence suggests very slow cooling rates. Together, this and other evidence have been used to propose the Acadian altiplano. To test this model and understand more about the evolution of plateaus, we integrated monazite and Xenotime geochronology and geochemistry with garnet and other major phases to explain pressure-temperature time paths from different crustal levels. Our petrochronologic approach first begins by mapping entire thin sections with the electron microprobe to identify monazite and xenotime in their microstructural context. We then map individual monazite and xenotime to reveal their internal zoning. We then date these individual zones or domains using the Kamika Ultrachron electron microprobe at the University of Massachusetts. For each domain, we acquire a date and a full composition. We also map and acquire quantitative data for major and trace elements in phases like garnet. We then integrate major and trace element thermobarometry, thermodynamic modeling, and Jercinovic to constrain the pressure-temperature time path. This simplified tectonic map highlights the location of samples we've analyzed in the course of our study. We won't have time to discuss all these samples today. Let's focus in on three areas that highlight the mid to upper, middle, and lower crust. Let's go through these from top to bottom, starting first with the Amherst Block. The Amherst Block is a Paleozoic inlier in the Mesozoic Hartford Rift Basin. Peter Robinson interpreted that it was dropped down during rifting and preserved higher crustal levels not exposed elsewhere in southern New England. Garnets are highly resorbed but show evidence for three compositional domains: a high calcium core, a low calcium mantle, and a high calcium rim, together indicating a complex metamorphic history. Thermobarometry suggests two metamorphic peaks in the silmonite field. Polyphase metamorphism is supported by complex zoning in monazite, which has up to 8 compositional domains, and Xenotime, which has up to 4 compositional domains. On the right, individual domains are plotted against chemistry. The yttrium in monazite and ytterbium dysprosium ratio, a relative factor of garnet influence in Xenotime. Reaction history analysis suggests that the high yttrium monazite domains are in fact in equilibrium with Xenotime, thus reflecting changes in temperature, while low yttrium monazite was likely in equilibrium with garnet. Xenotime domains increase the ytterbium dysprosium ratio letting garnet breakdown around 330 MA. Integrating this data together, we constrained temperature time and pressure time paths for the Amherst Block. These suggest one thermal peak around 400 MA related to the nappe phase of the Acadian orogeny. This was followed by rapid cooling, followed by a second thermal high around 380 million years ago, which was followed by relatively slow cooling. Now let's move deeper into the crust, into the mid-crustal rocks of the central Massachusetts metamorphic high. These rocks show abundant evidence for partial melt at all scales. Thermobarometry suggests an overall counter-clockwise looping PT path with prolonged mid-crustal residence at around 6 kilobars or 20 kilometers depth. Compiled uranium-lead dates for anatectic rocks suggest prolonged and abundant partial melting between 390 and 350 million years ago. Monazite generally show high yttrium cores, low yttrium mantles, and high yttrium rims. High yttrium cores are generally in the order of 380 MA or older, reflecting growth of monazite before garnet. Yttrium in monazite sharply decreases after 380 and is interpreted to represent the growth of garnet, which is a major yttrium sink. Low yttrium monazite grew between 380 and 330 million years ago, suggesting that garnet was stable and these rocks were hot and deep for as much as 50 million years. Notably, low yttrium monazite are associated with north-south orogenic parallel transpressive fabrics. High yttrium monazite rims, dated to 330 to 300 MA, are interpreted to represent garnet breakdown during orogenic collapse. Together, these suggest that the rocks of central Massachusetts were hot and partially molten for a very long period of time. Now, let's move on to the lower crust. We have two main sources of information on the lower crust of the Acadian orogeny. Keller and Ague and Ferrer et al. Have presented evidence for high-temperature granulates, recording pressures of 1.8 to 2 GPa and temperatures in excess of 1,000 degrees. These are disaggregated blocks in thrust slices in north-central Connecticut, and suggest that the lower crust of the Acadian origin was very hot. In addition, we've also identified high-pressure granulates exposed in gneiss domes in western Connecticut. Today we'll focus on these, as the structural context is preserved, and we have more chronologic constraints. These rocks also show lots of evidence for partial melting, and have garnets that are very large and compositionally zoned. Cores are relatively low in magnesium and high in calcium, corresponding to temperatures around 550 to 600 degrees Celsius with pressures around 10 kilobars. Garnet mantles are moderately high in calcium and very high in magnesium. These zones, along with phengite thermobarometry, suggest peak conditions of 16 to 18 kilobars and temperatures of 750 to 800 degrees Celsius or more. Finally, the rims suggest a period of near isothermal decompression with reequilibration in the mid-crust. Together, these indicate an overall hairpin-style PT path. Interestingly, these are very similar to PT paths from the North Himalaya and Pamir gneiss domes. Monazite from these samples are systematically zoned with increasing yttrium from core to rim. Low yttrium cores are approximately 375 MA, and interestingly, have very minimal europium anomalies. This suggests that monazite grew in the presence of stable garnet and minimal pelagic clays. Thus we can infer it grew at high PT conditions. Mantle domains are moderately enriched in yttrium and have oscillatory thorium zoning. Thus we interpret they grew from anatectic melts, likely during decompression. Finally, high yttrium monazite rims grew in equilibrium with xenotime during mid-crustal equilibration. Monazite and xenotime don't document the prograde path, but they provide a detailed record of the retrograde history of this rock. These rocks were exhumed from near the base of the Acadian crust into the mid-crust, perhaps by a channel mechanism. They experienced a long mid-crustal residence before being exhumed in core complex-style gneiss domes during orogenic collapse. From studying just these three regions, we can see distinct PTT paths for the mid to upper, mid, and lower crust of the Acadian altiplano. The upper crustal Amherst Block is the only to preserve the early phases of crustal thickening. Interestingly, the timing of melting on all these rocks is somewhat different. The Amherst Block, based on existing uranium-lead monazite dates from pegmatites and granites, experienced partial melting during the nappe phase. It did not melt at 10 to 15 kilometer depths during the plateau phase. In contrast, the mid-crustal rocks at 20 kilometers depth indicate abundant evidence for a prolonged partial melt between 380 and 350 million years ago. Interestingly, these are the depths where Nelson et al. Imaged bright spots, often interpreted as partial melt. It's possible that this region represents an exhumed bright spot. High temperatures and abundant partial melt may be part of the rheologically weak structure of orogenic plateaus. Thus, we conclude that these PTT paths are independent supporting evidence for the Acadian altiplano. We can take slices through these PTT paths to reconstruct the thermal and crustal structure of the plateau at certain periods. This cross-section illustrates the overall thermal structure of the plateau constrained by thermobarometry. The upper mid-crust is characterized by amphibolite phase sheets rocks, while the mid-crust is characterized by high-temperature granulates. High-pressure granulates in the lower crust record high temperatures to ultra-high temperatures. These are consistent with evidence from the Himalaya, exhumed xenoliths from the Tibetan Plateau, and the thermal models of the Jameson and Beaumont group. An intriguing similarity between their models and our observations are relatively compressed isotherms in the mid and lower crust, and temperatures that permit types of channel flow. Two major types of channel flow have been hypothesized for the Himalayan Tibetan origin. One, proposed by Chris Beaumont, suggests mid-crustal flow perpendicular to the origin, extruding the greater Himalayan sequence. Another type of channel flow was proposed by Clark and Royden. Their model proposes outward flow of Tibetan lower crust parallel to the origin. Fully evaluating whether these two types of channel flows occurred in New England is a work in progress. However, based on our observations, we might suggest a third type of channel flow occurred, with origin parallel flow in the mid-crust. This horizontal flow with a vertical fabric may have balanced shortening. This may have helped to balance forces involving tectonic convergence, ductile gravitational flow, and erosion. We constrained PTT paths from the upper, middle, and lower crust of an ancient orogenic plateau, and show how this area can be used to test models and study the evolution of modern orogenic plateaus. Thank you.
Okay, thank you very much. That's a great talk. We've probably got time for one or two quick questions. You've already answered the one in the chat. I do have. Oh, have we got another talk? Yeah. So, Catherine Mottram asks, monazite grown in equilibrium with xenotime is enriched in yttrium. I always assume that monazite grown with xenotime would be depleted in yttrium. Do you have any insight into how yttrium would partition between monazite and xenotime?
Yeah, so it's in all of our samples, it's consistent with a mostly temperature dependent partitioning, like the classic thermometers that are calibrated by Heinrich et al. or suggested by Pyle et al. So they, in some samples, we see they generally really well tracks the retrograde cooling, and in some samples we get some constraints on the prograde heating path as well, which agree with and the monazite xenotime thermometry using the Heinrich et al. Calibration ended up being really consistent with the thermodynamic modeling and traditional and trace element thermobarometry, and as well as argon 4039 thermochronology. So if they're in equilibrium, monazite and xenotime, then the yttrium content's a really great thermochronometer as well, at least in my opinion.
Don't see any more questions. I've got one comment myself, which is more related to tectonics rather than metamorphism. You use the Himalaya-Tibet collision as an analog, but there we have ongoing convergence of a large, old craton indenter, whereas my understanding of the Appalachians is that you don't have such a big indenter, but we also do have plateaus in the Andes, and I guess it's really a comment really that the Indian-Asian idea of forming orogenic plateaus is not the only way to do it.
Yep, totally. In the paper we talk about, our paper in EPSL, we talk about that possibility a little bit. At least it maybe starts as a collision, and then one possibility is that idea from Case Van Staal is that subduction steps back outboard after the collision of the Maguma terrain in Nova Scotia, and then that sets up sort of an Andean style retroauric plateau. So that's one possibility. There's definitely a lot of evidence for at least for a long time. It's been the multiple collisions have been associated with the Appalachian origin. But yeah, it's an interesting question to think about in terms of, you know, if there was a plateau in New England, the scale may have been smaller, more the size of the Andean altiplano versus the Himalayan plateau, and that could be related to a smaller indenture.
Yeah. Okay, thanks so much.
Thanks.